Hello there and welcome back to this video series on control systems. Over the past few classes, we have been looking at spring mass damper systems and RLC circuits. We have also derived transfer function of spring mass damper systems and RLC systems. Basing on that knowledge, we'll try to build on and specify what are analogous systems and try to strike analogy between mechanical system, that is SMD, spring mass damper system, and electrical networks. To continue into this class, it would be best if you go back and watch videos 16, 17, 18 and 19 before going into this video. It would also help if you go back and solve a few problems on electrical circuits and mechanical systems before going into this class. With that, we will go into this present class and say that analogous systems are systems that are, although physically different, can be represented by the same or similar type of differential equation. That is, the same terms fall together in same place. Put in the context of our study, that is control systems, we can say that analogous systems are systems that have the same or similar transfer function. Since we are talking about electrical networks, RLC circuits and mechanical systems, we would term it as electromechanical analogy. To begin the topic, let us consider a simple RLC circuit, resistor, inductor, capacitor circuit, where elements are put in series, excited by a voltage V of T, with bracket T indicates time domain, I of T. For such a system, we can very easily write that the total voltage drop is the drop across resistor, plus drop across inductor, plus drop across capacitor. And thus we can write the equation as Ri is the drop across the resistor, L di by dt is the drop across the inductor, 1 by C integral I d tau is the drop across the capacitor. We define I current is equal to rate of charge dq by dt. With this definition, we can write down V of t is L d square q by dt square plus R dq by dt plus 1 by C q. This is one side. The other side is a mechanical system which is shown over here. For this system, Ft is the force which we can consider to be the input, and then x is the displacement which is the output. When we say displacement, we may mean velocity x dot of t or acceleration x double dot of t. In either case, we can see that the elements B, K and M are in parallel. With this, we can write down an equation of motion as shown over here. F of t is m into acceleration plus b into velocity plus k into x of t. It is here we can see that there is a second order term, first order term and a zeroth order term. And we can also see that g of t and f of t are in comparable places on the left hand side of equal to sign. Similarly, you have x of t and q, that is the zeroth order derivative, x of t and q, they are in similar places. So x in mechanical system is analogous to charge in the electrical system. Similarly, we can also see that inductance L is corresponding to mechanical mass M. Similar way, we can see resistor is comparable to a damper because they occupy corresponding similar positions in the describing equation. Similarly, inverse of capacitance is analogous to the spring in the mechanical system. So to sum it up, we will say that this electrical circuit is analogous to this mechanical system. You can very clearly see that elements are in series here, whereas elements are in parallel here. That is, series parallel connection is reversed. Also, we can say that since we are striking analogy between force and voltage here, force is on the left hand side, voltage is on the left hand side. So we call it force voltage analogy. Sometimes we call it direct analogy also. So you can see force is analogous to voltage. F of t is analogous to V of t. Similarly, you can see the other term, mass is analogous to inductance. Mass is analogous to inductance. Similarly, damping, a damper in mechanical system is analogous to resistor. We can also see this from another angle. Resistance also dissipates energy, damper also dissipates energy. Another quantity 1 over C is analogous to the spring stiffness K. 1 over K is analogous to K. I have put it in red here to indicate that inverse of capacitance is analogous to spring stiffness K. And finally, we have displacement X analogous to charge Q. Thus, we can summarize that force voltage analogy is an analogy in which series arrangement in mechanical systems gets represented by parallel arrangement in electrical systems and vice versa. This force voltage analogy is sometimes also called direct analogy, in which force is analogous to voltage, displacement is analogous to charge, mass is analogous to inductance, spring stiffness is analogous to inverse of capacitance, damper is analogous to resistance. That's all we have for now. Have a great day.